In part 2 of the Unit 10 notes, we are going to be covering Boyle's Law and Charles' Law calculations. In 1662, Robert Boyle developed Boyle's Law, in which he described the inverse relationship between the pressure and volume of a gas when the temperature remains constant. He designed experiments similar to the one that is shown below. So in this image, we can see that our temperature is constant. It's 300 Kelvin in the beginning and 300 Kelvin at the end. Here, our piston is a little bit higher up, so we have a greater volume for our gas molecules with a pressure of 1 atmosphere. When the piston is pressed down, our volume is cut in half. And from here, we can see that our pressure is increasing, and it actually doubles. The law that we can use here is that pressure times volume is equal to a constant, K, or what we will be using for our calculations, our pressure 1 times volume 1 is equal to our pressure 2 times volume 2. You can also think of these as initial pressure and volume and final pressure and volume. In our first checkpoint question, we have a balloon which contains 30 liters of helium gas at 103 kPa. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25 kPa, assuming the temperature is constant? The fact that the temperature is constant here is the reason why it is not present within our calculation, so we're only going to be looking at pressure and volume. Now there is a specific way that I want you to set up each of these problems, and this is the way that you will be evaluated for it on your test. You must write down each of the variables. So we have pressure 1, volume 1, pressure 2, and volume 2. A balloon contains 30 liters at 103 kPa. So I have 30.0 liters, 103 kPa. What is the volume? So I'm looking for the final volume here, where the pressure is only 25.0 kPa. So step 1 in what I want you to be writing out is just identifying each of the variables. So I want to make sure that you're not mixing up any of the pressures and volumes. Now from there, I would want you to write out the equation. Eventually you'll have a whole bunch of different equations and you'll have to make sure that you're picking the right one. So since we are clearly covering Boyle's Law here, I'm going to write down Boyle's Law. Next, you must identify which of the variables you are trying to solve. Here, I want to isolate V2. I want this letter by itself. So you need to show the manipulation of this equation to get that letter by itself. Here, that means dividing both sides by P2. I now have a new version of this equation. V2 is equal to P1 V1 over P2. And from here, you would plug in each of your numbers with the units. My pressure 1 is 103 kPa. My volume 1 is 30.0 liters. And my pressure 2 is 25.0 kPa. Now if you did this correctly, the unit should cancel out here. So kPa cancels with kPa. I'm left with liters, which is an acceptable unit for volume. There are times where your pressure units might not match up. Maybe one of them is in atmospheres and the other one is in kPa or psi. At that point, you would need to use one of the conversion factors, which was demonstrated in the notes video part 1, in order to make the units the same. But here everything matches up, so all I need to do is multiply and divide across, and then round for the correct number of significant figures. Now my original answer here comes out to 123.6, but I need to round for 3 significant figures. So I'm going to record this answer as 124 liters. For our next Boyle's Law problem, this time we are using nitrogen gas in a sealed container. It's exerting a pressure of 1900 torr. When the pressure is changed to 1.70 atmospheres and the new volume is 500.0 milliliters, what was the original volume? So just like before, I need to identify each of the variables that are either given or are asked for. Okay, we have a sealed container. It's exerting a pressure of 1900 torr. When the pressure is changed to 1.70 atmosphere, the new volume is 500.0 milliliters. So these two numbers belong on the same side of the equation. What was the original volume? Now here, just like I mentioned on the previous slide, I have a potential problem. My torr and atmospheres are not compatible with one another, so I need to convert from one to the other. Now it doesn't really matter which one I convert because the unit is going to cancel out in the end anyway. When I solved this problem, I went from the 1900 torr and I converted that into atmospheres. So torr on the bottom, atmospheres on top. 1 atmosphere is 760 torr. So that comes out to 2.5 atmospheres. So when I plug this into my equation later, I'm not going to use the 1900 torr. I'm going to use 2.5 atmospheres instead. All right, from here, I identify the law that I'm using. So we're still just on Boyle's Law. So this is what we have. And this time we were trying to solve for volume 1. That means dividing both sides by pressure 1. And now I have a new version of this equation which I can plug into. So volume 1 is equal to P2V2 over P1, and I can plug in my numbers. It's going to be 1.70 atmospheres, a volume of 500.0 milliliters, and a pressure of 2.5 atmospheres. I'm going to multiply and divide across. I have 340 milliliters. This is two significant figures, which matches the two significant figures from the 2.5. All right, our second law that we are going to be discussing is Charles' Law. In 1787, Jacques Charles developed Charles' Law, in which he described the direct relationship between the volume and temperature of a gas when the pressure remains constant. So this time, since pressure is constant, that variable will not be found in our equation. He designed experiments similar to the one shown below. In order to perform calculations using this law, all temperatures must be in Kelvin. To convert from Celsius to Kelvin, all you have to do is add 273. So in our experiment that we see here, we have a certain amount of volume that our gas is occupying. We have this piston, but there's no pressure being applied to it, so it can freely move up and down. When we add heat below, the molecules are going to move faster, they're going to apply more force to the sides of their container, and they're going to cause this piston to rise. So since our pressure is constant here, 1 atmosphere the entire time, the volume of the container has to rise in order to compensate. Similar to before, we have two versions of this equation. Volume over temperature is equal to some kind of constant, which over here you could see was our constant of the pressure remaining constant. Or you could say your volume over your temperature is equal to your volume over your temperature. All right, for our first checkpoint question, a balloon is inflated in a room at 24 degrees Celsius and has a volume of 4.00 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if the pressure remains constant? So I'm going to write out each of my variables. This time I have volume 1 and temperature 1, and then I have volume 2 and temperature 2. My volume 1 is 4.00 liters. Now for my temperature 1. I typically never write any temperatures that are in Celsius within this spot, because then I'm more likely to accidentally plug it into the equation. So I usually just add 273 directly if I notice that my temperature is starting in Celsius. So if I were to add 273 to this temperature, that would be 297 Kelvin. So that's what I'm going to plug in down here, 297 Kelvin. I'm looking for the new volume, so that's my question mark. And then for my temperature, if I add 273 to this, that would come out to 331 Kelvin. Just like before, I'm going to write out my equation and then solve for the missing variable, but this time I'm using Charles' law. I'm going to get volume by itself. To do that, I can multiply both sides by temperature, because then the temperature would cancel out on this side. So this is a new version of my equation. V2 is equal to T2 V1 over T1. And now I can plug in each of my numbers. My T2 is 331 Kelvin. My V1 is 4.00 liters. And my T1 is 297 Kelvin. My Kelvin is canceling out. I'm left with liters, which is an acceptable unit for volume, so I know that I set everything up correctly. Going to multiply and divide across. I have 4.46 liters. And this three significant figures matches with the significant figures of each of my values here. In our second Charles' law calculation, this time we have a gas occupying a volume of 455 centimeters cubed at 20 degrees Celsius. We're looking for the final temperature if it occupies 742 centimeters cubed. Assume that pressure remains constant. So I have volume and temperature, volume and temperature. My initial volume is the 455 centimeters cubed. And the temperature, again, I'm going to add 273 to this, so that's going to come out to 293 Kelvin. My volume was 742, and my temperature 2 is unknown. Now, I didn't mention this before, but you can actually also end up with different units of volume. Commonly, you might see this with milliliters and liters. If that ever happens, you could simply do a one-step metric conversion, which we covered back in Unit 1. But this time our units are the same, so we don't have to worry about that. We're using Charles' law, so that's V1 over T1, which is equal to V2 over T2. This time I want T2 by itself. Now there are a few potential ways that you could solve this. I often have students that will start by dividing by V2 on either side. And that does get you T2 by itself, but what you actually solve for is 1 over T2, which is not the same thing. Now, there is a way you could fix that. You could flip both the numerator and the denominator on either side and come up with a valid equation. But this often confuses students, so I'm going to show you what I believe is a simpler way. You can start by cross-multiplying. So I'm going to multiply the T2 up to the opposite side and the T1 to the opposite side. I end up with V1 T2 equals V2 T1. Now that all of my variables are in a straight line and none of them are in the denominator, it should be a little bit easier to solve for my missing piece, which is T2. I divide both sides by V1, and that's my answer. This is the same version of the equation I would have gotten if I initially divided both sides by V2 and then flipped both the numerators and the denominators. So I'm going to rewrite my equation here. T2 is equal to V2 T1 over V1. And then I'm going to plug in each of my numbers. My V2 is 742 centimeters cubed. And my T1 is 293 Kelvin. My volume one is 455 centimeters cubed. The centimeters cubed is going to cancel from the final answer, and I will be left with Kelvin. My final answer here for three significant figures is going to be 478 Kelvin. Now in this question, it did not specify what what unit the temperature had to be in, so I can leave this answer in Kelvin here. Just make sure that if you're completing any practice assignments, that if it asks you to record the temperature in Celsius, you then subtract by 273 to get back. But otherwise, I can leave my answer here in Kelvin. That concludes our part 2 for the Unit 10 notes. When we come back in part 3, we will be looking at Gay-Lussac's law and the combined gas law.